Suppose now that we have a coin, but we do not know whether it's fair, right? So maybe the coin is biased with probability P. And what we want to do is we want to estimate what P is by flipping the coin many times. So if we flip the coin n times, then the fraction of heads is going to be the amount of heads divided by n. And the amount of heads, we saw that this follows a binomial distribution with parameters n tosses and probability p of heads. And so this will give us the fraction of heads that we will observe. And the point is, how many times should we toss the coin so that we can guarantee that this fraction that we're observing, say, is within, let's say, 5% of the true probability. So you can think this would help answer questions like, if I have a coin and I want to test whether it's fair or not, how many times do I need to toss it, right? So let's do that. So let's use Chebyshev to bound the error, right? So we're interested in estimating P, so we would like this to be close to P, right? And so what we want is, what is the probability that x minus P, or sorry, x bar here minus P is larger or equal than some value epsilon is smaller or equal than delta. So we would like to say that when we throw n many times, we would like that the probability that this is further away than a certain number be small, right? That's what we would like to happen here. Well, to apply Chebyshev, what we need to do, we need to compute the variance here. So, of course, the expected value of this here is just going to be the expected value of x over n. And we already saw that the expected value of a binomial with parameters np is np over n. So this is just p. And so with this, we're ready to just apply Chebyshev. And for that, we need the variance. So now what is the variance of x hat? Well, the variance of x bar, the variance of x bar. So we saw that the variance is multiplicative, but it goes out with the square. So the variance of x divided by n is going to be the variance of x divided by n squared. And we already saw the variance of a binomial is np1 minus p, and so this is divided by n squared, which means that the variance is going to be p1 minus p over n. And then by Chebyshev, so if we take Chebyshev's inequality, we will get that the probability that this is further from its mean than a certain epsilon will be less or equal than the variance, the p1 minus p over n, divided by that epsilon squared. Which means that, and you could, how do you say, bound this, if you want to simplify, make it even looser, by 1 over n epsilon squared, for n epsilon squared, right? So p1 minus p, the biggest value that it can assume is 1/4 when p is equal to half. And so you can just bound it by this amount here. So with that, we can have that the probability that this is further away than a certain epsilon is less or equal than 1 over 4n epsilon squared, and just depending on n. So let's use this. So let's choose n for a specific guarantee. So suppose that we want an accuracy of 5% with at least 99% confidence, or a delta equal to 0.01. So then we want that fraction that we found. So we want this 1 over 4n epsilon squared. So we want our epsilon to be this, and we want this to be less than the delta, to be less than 0.01. And this tells you that if you solve for this, it tells you that n has to be larger than 10,000, right? And so what this means is that Chebyshev guarantees that if you do 10,000 coin flips, this is enough to estimate P within 5% with probability at least 99%, right? In other words, I can write it here. This means that the probability that the distance between the fraction you observe and the actual probability of the coin, that this distance, the probability that this distance is larger than 0.05 is going to be larger or equal than 0.99. That means that the probability that this distance is less than 0.05, so the probability that this is very close, within 5%, is going to be more than 99%. So this is a conservative guarantee, right? In practice, fewer tosses may often be enough, especially if we use sharper inequalities. This is just showing how Chebyshev can be used, but there are other inequalities that can be stronger when doing these problems. The advantage of Chebyshev is that it's very general. It only uses the variance, and it gives a safe bound without needing detailed information about the distribution. And so the main takeaway here and of this whole lecture is that the variance measures the spread, and Chebyshev turns variance into a bound on large deviations.